All right, so I want to go through our third version of Quiz 2 and use it as a way to sort of connect all of the ideas about limits, the algebraic, the graphical, and then tying in one we haven't talked about, which is tables, and why I didn't talk about it in class, but why it is important for this sort of video wrapping most of our limit stuff up. Of course, I will post all of those other videos about all the notes that I handed out, but let's just start here. So get out of here. There we are. So let's just go ahead. If we see a rational function, as we did in our quiz, as we will do all the time, first thing I would do is factor it up so we have the other form of it. So it looks like the numerator we can factor out of 4 as our greatest common factor, leaving behind an x plus 4. And in the denominator, we have our difference of squares, which I love, x plus 4 and x minus 4. These are leveraging our conjugates. All right, so there's our rational function. We also immediately see it appears that we can cancel that one common factor from our numerator and denominator, or realize it's just a fancy pants way to write 1. So we could write a new version of this that's even simpler than the previous 2, which is just 4 all over x minus 4. And if we really want to bring it way back, thinking about our first day of class, we could really think about this as a shift of 4 to the right with our little stretch going on, because right, we can actually see the transformations that would happen. I'm going to write down that x cannot equal negative 4. All right, so then let's fill in all this information before we pop in a graph. So the thing that we just canceled, that common factor from our numerator and our denominator, that is what gives us our whole. So we look at this, we go, okay, that's going to tell me where the whole is, which happens at the negative 4. And if we plug negative 4 into the function that we're not allowed to, the new function, we're going to figure out where that little open circle needs to be. So if I plug that in, we'll get 4 all over negative 4 minus 4, which is 4 over negative 8, or negative 1/2. So there is my whole. Plug in your value into the simplified version of your rational expression or function to find the y value of the whole. Now, our horizontal asymptote. In this case, this is where I want to connect our algebraic pieces. When we're talking about a horizontal asymptote, we're talking about, right? Let me go ahead and do this. We are talking about the limit as x goes to infinity, right? Our limit's at infinity. What happens as my x gets really, really, really large with my function? And we're now looking at this function of 4 over x minus 4. Now, if we want to be really good about the algebraic reasoning for this, right, that analytical limit, we can sit there and be like, okay, let me multiply top and bottom by 1 over x, multiply by this fancy pants version of 1. And then we can rewrite our limit. And this will be 4 over x. And we distribute it to this bottom binomial. We get 1 minus 4 over x. And one thing we do know is the limit of 1 over x, as x goes to infinity, is 0. These are multiplied by a constant of 4, but that doesn't matter because that just means it's 4 times 0, right? And we saw those limit laws. So this is 0, this is 0. We're not really writing that yet, but we can think about it in our head, and then we can go, okay, well, this I'm allowed to say is 0. Notice there's no x, so I've got rid of my limit notation, over 1 minus 0. 0 divided by, come on, you can write a 0, divided by 1 is just 0. So our horizontal asymptote is happening at y is equal to 0. Back in when you're in pre-calculus and we don't have limits, we sometimes will just look at this and come up with a bunch of rules. If the degree in the denominator is bigger than the degree in the numerator, our horizontal asymptote is y is equal to 0. But this is the technical reason why. I could write the other side of that limit as well, right? The limit as x goes to negative infinity of our f of x, I'm not going to write the whole function because my pen does not like me, is also equal to, that's a negative, I can't tell, going to be equal to 0. For same reason. So there we go. We've got a horizontal asymptote. Vertical asymptote, this is all about when our function is going to go a little bit off the wall. And so in this one, we're going to look at our denominator of our simplified function, and we can see when x is equal to 4, problems are going to happen. We're going to be trying to divide by 0, and 4 divided by 0 doesn't work. And we're going to play around with this a little bit more. We also have our y-intercept. Y-intercept happens when we plug 0 in for x. So I have another color. Let's do this. Y-intercept. F of 0 is 4 all over 0 minus 4, which is 4 over negative 4, or negative 1. In this case, we do not have an x-intercept. Typically, that would be when our numerator goes to 0. We would set this whole thing equal to 0 and then solve, but there's no way to get that to happen with this particular function. So this doesn't exist. Okay. So let's just start with my little function graph, and then let's talk about those graphs, the limits with tables, the one thing we haven't, come on computer, the one thing we haven't done yet. I always wonder what happens to my video when I try to do a print screen, because your whole screen freezes. So what happens when I'm taking a video to me? I'm never going to watch the video to find out. So someone can tell me. There she is. There's my graph. All right, so let's go ahead and put all the information we have here, and then we'll talk about the tables. So we've got a horizontal asymptote at y is equal to 0. We have a vertical asymptote at x is equal to 4. Oh, there's that shift to the right. You see what I'm saying? We have our y-intercept at negative 1, and we have our whole at 4 and 1/2, negative 4 and negative 1/2. So let's pretend we didn't really understand where all these limit things were going. And let's say we had something that said, hey, let me look at, let's do first the vertical asymptote. If somebody said, let's figure out what the limit as x approaches 4 from the right is. I want to show you what we used to do when I was in school, what a lot of textbooks still really want you to do, and what your first question on this week's knowledge check is in Delta Math, is we used to have to come in here and say, okay, well, probably, hopefully, at least have a calculator where I can put in the function, so I don't have to keep redoing this. And let's just type this in. We've got 4x plus 16, boom, divided by x squared minus 16. Might as well use the full version. That way, if you screwed up anything with factoring, you'll find out pretty quickly if you have the original as your actual input for your function. And we're going to go to our, I guess we'll do table. And let's just have it ask for independent variables. That's what we'll do. So you can do this in the TI-36X, you can do this in this calculator, you can do this in the Inspire, you can do this in Desmos. So I'm just going to do it in this calculator because this is how I suffered when I was a student. So if we want to approach 4 from the right, if we want to come in and approach that value of 4 from the right, what we did when we used to do this in class is we'd say, okay, well, let's choose a number close to 4 on the right-hand side of 4. Let's try like 4.2. Okay, y is 20. I'm going to put that on my graph. Let's get closer. Hopefully we agree 4.1 is closer to 4 than 4.2 was. Oh, it got bigger. Let's get even closer. What about 4.01? Oh, it's getting huge. 4.001. Right? If we plug in the actual value of 4, it's going to tell me error, but if I keep plugging in values closer and closer to 4, I can see this thing is going off towards positive infinity. So if I wasn't 100% sure about where this thing was going, I know it's going up this way, right? In fact, it's way steeper even than that because we just saw, whoop, and we know we got to approach that. So there is my first part of my graph. Now, I talk a lot about multiplicity and changing of signs. We're going to see this very soon when we start playing with our plus minus tables. But I know this is happening. Again, if I didn't know that, this is equal to infinity. If I wasn't sure, I would be doing the same thing, approaching from the left. So same idea. This hates me. If I want to approach from the left, I'm just going to start with, say, like 3.9. That's just to the left of 4. And then I want to get closer. 3.99. Oh, it's getting really big and negative. It seems like that's going to be my negative infinity. And then whoop, whoop, whoop. So there's my graph. And that really makes sense if you think about our parent function of 1 over x. It has that same shape. The only difference is we have a hole. We have that vertical stretch that we can't really even see in our sketch. And then we also have the shift of 4 to the right. Now let's look at the hole. Hole would be the same business, right? If we're talking about the hole. We look at the limit as x approaches. We need to do left and right, so let's actually do -4 from the left. Let me clean up that notation. X approaches -4 from the left of my function. And let's see what happens. We can see here that it's going towards that -1/2. We know algebraically it's going towards -1/2 because we eliminated that common factor, right? We canceled it out as a 1 or whatever we want to call it, and we plugged in, we direct substituted and got that 1/2. This was our direct substitution, right? If we had the algebraic pieces and steps here, that would have been our final step. But let's just see it in the calculator. So again, we're going to come from the left. So that means we're going to start with something, let's even try -5 as our first value. It's definitely to the left, -5. Pop. Okay. Let's get closer. -4.5. Let's get closer. -4.9. Let's get even closer. -4. My gosh, I went the wrong way. I went the wrong way. 4.0. I was like, wait a minute. -4 is, of course, an error. Don't listen to me. -4.1. We need to get close to -4. I got closer to 5. -4.01. -4.001. And the nice thing is, if you're actually approaching a value that's not infinity, at some point, if you keep typing in values that are really, 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 really close to 4, but not quite 4, your calculator is going to give you the actual value of -1/2 because you're hitting machine rounding where it can't even process the difference between the value and what you put in. And we could see the same thing from the other side. If we do -3.99999, as close as we can get from the right, also 1/2. So this is the table version of the graph version of the algebraic version. So we kind of have seen all the different pieces and how they relate back, and why I love this rational function stuff, because it's really got everything. The only thing it doesn't have is our jump discontinuities that we saw in class.